All right, so welcome to part three of the lecture series on Introduction to Computer Networks on the topic of transport and application layer.
All right. So now we'll look at a few of these important fields which are included in the TCP header. So the first one that is going to be discussed is the sequence number. In short, we also call it the sec number. And this is a very important value that is used to check the integrity and the security of TCP communication. So the sequence number is a 4-byte value, which means the maximum value in integer that could be assigned to a sequence number cannot exceed 4 bytes. So we already know that in TCP, all messages are divided into segments or datagrams, and both of these terms are okay. So when a message is being divided into these segments, each of these segments are assigned a sequence number. And the number is actually based on the starting byte value of the original message. So let's say we have a file that is a total of 4,500 bytes, and we say that this file is going to be divided into 3 segments, each of 1,500 bytes. Then the sequence numbers for these 3 segments are going to be 0, 1,500, and 3,000. So if we would like to visualize it, so let's say our file is 4,500 bytes, and this is byte number 0, this is byte number 1,500, this is byte number 3,000, and this is byte number 4,499. Then given that we have already said that this file is going to be divided into 3 segments, then the first segment will have its sequence number equals to the beginning byte number, that is 0. The second segment will start with byte number 1,500, so the sequence number is 1,500. Similarly, the third segment will have its sequence number based on the starting byte number, in this case 3,000. So now, if you look at each of these segments, the first segment will contain byte numbers 0 to 1499. The second segment will have 1,500 bytes in total, but the number assigned to the bytes would be byte number 1,500 till byte number 2,999. And the third segment, similarly, will be a total of 1,500 bytes, but starting with byte number 3,000 till byte number 4,499. Another thing that should be kept in mind is that the initial sequence number, instead of starting at 0, it is randomly generated. And if you want to look at that, the way it works is that, let's say, again, we have 4,500 bytes, and it starts with 0, then 1,500, then 3,000, and here we have 4,499, and our sequence numbers are 0, 1,500, and 3,000. So now we add a random value to the initial starting value. And it is the same value that is added to all the sequence numbers. So when you are doing the calculations, you can just discard the value of R and you will have the original value that you are considering for the byte numbers. But this random value is added to all of the sequence numbers, and this is the same number. And the reason why we do it is because this helps us prevent something that we call man-in-the-middle attacks. And in this case, an attacker tries to interfere between two communicating parties and tries to guess the sequence number of a segment. So instead of starting at 0, 1500, 3000, just to keep it varying, we assign a random value R added at the beginning of the communication, and this is only known between the two parties. So when you are doing the calculation at the two ends, the random value is just subtracted and you get the original value. So this is what the sequence number is. The next number that is also very important in verifying the integrity of all TCP communications is something that we call acknowledgement numbers. And in short, this is called an ACK number. So what happens is that the receiver, whenever it receives something, the destination sends an acknowledgement that, okay, I have received so much of the data that you have sent. And this is a communication between the sender and the receiver, which ensures that all of the data that is being sent over is actually being received by the receiver and is not being lost on the way. So the acknowledgement that is sent from the receiver back to the sender includes the ACK number. And the way that this ACK number is generated is actually pretty simple. It is just one greater than the maximum sequence number that has been received so far. So if you are sending over 10 bytes, the ACK that is expected by the sender is 11. And this implies that the destination has received that many number of bytes so far. And the eventual result is that it allows the recipient to confirm the receipt of the several segments which are being sent one after another by the sender. So we'll look at a few examples. So going back to the previous numbers that we already looked at, let's assume that we have 3 segments of 1500 bytes each that is to be sent by the source. The sequence numbers, to keep it simple, we are discarding the random value R and we are only considering the original value. So the sequence numbers are 0, 1500, and 3000. So when these 3 segments are being sent by the source, there are many possible cases in the process of delivery and also the resulting acknowledgement. So the first case is that destination receives segment 1, that's the first segment, which starts with sequence number 0. And we know that the first segment had bytes 0 till 1499. So the ACK that is sent back from the receiver to the sender should have the ACK number 1500. So this is just plus 1 from the max value that has already been received. Now let's look at the second case. For example, two of these segments have now been received at the same time by the receiver, and we know that this means that the segments had byte numbers 0 till 1499 in the first segment, and in the second segment it had byte numbers 1500 till 2999. So the max value that has been received so far by the receiver is 2999. So the ACK is just plus 1 to that, which would be 3000. So now let's look at a slightly more complex scenario. So let's say all of these three segments are being sent at the same time. However, the destination only receives segments 1 and 3. So in this case, it sends the ACK in terms of the maximum continuous value that has been received from the beginning of the file. So the first segment had 0 till 1499, and the third segment had 3000 till 4499. So the middle part is actually missing. So therefore, the maximum value that is received from the beginning of the file by the destination is 1499. So plus 1 to that would be 1500. And this is the ACK number that is returned by the receiver to the sender. So once the sender receives this ACK 1500, it now understands that the second segment actually went missing on the way. So what it does is that it retransmits the second segment. So the second segment, when it arrives, it now contains byte number 1500 till 2999, and now the receiver has the max value till 4499 because it had already received it before. So it just responds with the maximum value that it has already received plus 1. So in this case, it will be 4500 to indicate that it has received segment 2 and it had already received segment number 3 before. And if you look at the diagrams here, so the sender, a total of 4500s to be sent over, and this is the total file divided into the three segments. So segment 1, byte numbers 0 till 1499, a length of 1500 bytes starting with sequence number 0. Then segment 2, byte numbers 1500 to 2999, which is a length of total 1500 bytes. And the sequence number is the starting byte number, in this case 1500. And segment 3, byte numbers 3000 till 4499, that is a total of 1500 bytes, and the starting value is 3000. So now, if you consider example 1, the sender is trying to send over these three segments to the other party, the receiver. So when it sends over the first segment, this is segment 1. It starts with sequence number 0. The receiver receives this, and the total continuous bytes it has received so far is 1499. So it will now send over an ACK that is plus 1 from the total bytes that it has received. So 1499 plus 1 is 1500. Next, The sender sends over the second segment. This is segment 2, starting with a sequence number of 1500. The receiver receives segment 2, and in this case, the continuous bytes that it has received is 2999. So therefore, it's going to be plus 1 to this max value, which is 3000. And finally, segment number 3 is sent over by the sender, which starts with sequence number 3000 and contains 1500 bytes. So the receiver receives segment number 3, and the maximum value of the byte number that it has received so far is 4499. So the ACK is going to be plus 1, which is 4500. So in example 2, the sender sends over 2 segments at the same time. So this is segment 1 and this is segment 2. So the receiver receives both of these at the same time, and the max value that it has received is till 2999. So the ACK is going to send is plus 1, which is 3000. So the sender understands that the receiver has received all the bytes starting from 0 till 2999. And it needs to send the next packet starting with sequence number 3000. So segment 3 is now sent with sequence number 3000. So the receiver receives segment 3, and now the total continuous bytes starting from the beginning is 4499. It sends plus 1 as the ACK value, which is 4500. So now let's go to example 3. The sender sends all the segments at the same time. So this is segment 1, segment 2, and segment 3. However, the receiver receives the first segment and the third segment, and the second segment is actually dropped on the way. So one thing that you should note here is that starting from the beginning of the file, the maximum value that it has received so far is 1499. It doesn't really matter how much it has received over here. It's going to be stored, but for calculating the ACK value, the max is used plus 1. So therefore, the ACK that is going to be sent is 1499 plus 1, that is 1500. So the sender, when it receives an ACK of 1500, it understands that all the bytes starting from 0 till 1499 has been received by the sender, and the byte number 1500, the segment starting with byte number 1500 has not been received. So something got lost in the way. So it needs to retransmit segment 2. So it will now retransmit segment 2 again, starting with the sequence number 1500. So now the receiver receives segment 2, and now if you notice, the maximum value that it has received in continuous sequence starting from the beginning of the file is 1499. So the ACK that is going to be sent is plus 1, that is 4500. So it may not always be the case that all of these segments are divided with equal sizes. So in this example, we say that a client and a server are two parties which are communicating, and the client is sending the segments with different sizes. So for example, the first segment starts with sequence number 1 and has a total of 669 bytes. So the server will receive this segment and will add 669 with the sequence number and send it over as the ACK. So when the client receives the 670 in the ACK, it now understands that this is supposed to be the next byte number that the server is expecting. The length could be different, but the sequence number must be 670. And in this case, the second segment is of length 1460, which is then sent over to the server. The server receives it properly and then adds 670 to the number of bytes that it just received, which comes to 2130. And this is the ACK value that is sent over to the client. So now the client must start the next segment with the sequence number 2130. And in this case, the length of the segment is again 1460 bytes. The server receives it, then takes the sequence number it just received, adds it to the number of bytes that was received, and then sends it over back to the sender. And this continues until the TCP connection is closed. So if we look at actual scenarios of how things work, so let's say we have two parties communicating with each other, host A and host B. The first segment starts with sequence number 92, which is of length 8 bytes. The next sequence is 100, because 92 plus 8 is 100, and the length is 20. The next would be 100 plus 20, 120, and the length is 15 bytes. So 120 plus 15 is 135. And this segment is of length 6 bytes. So 135 plus 6 is 141. And the length of this segment is 16 bytes. So when all of these are being sent at the same time, the receiver, in this case, doesn't receive the second segment. So starting from the beginning, starting from 92, the max value that it has received is actually 99. So the ACK is sent as 100. It doesn't really matter if the others are received. So whenever it receives any of the others, it just keeps on retransmitting the same ACK value to tell the host that please retransmit the segment starting with sequence number 100. So host A, whenever it receives the ACK 100, it understands that one of the segments was dropped on the way, so it waits for a certain time just to make sure that if it is still going, and when the timeout expires, it then retransmits the segment with sequence 100. In another case, it may also be the fact that the ACK packet is actually lost. So what would happen in this case? So let's say host A sends over a segment starting with sequence 92 and of 8 bytes length. So the ACK that is received, that is sent over by host B is 100. However, in this case, we say that this ACK is actually lost on the way. So host A never gets to know if host B received this segment properly or not. So instead of just trusting the network, it waits for a timeout period, and if an ACK doesn't arrive, it then goes forward and retransmits the same segment. And this is just to make sure that none of the segments which are being sent from host A to host B is actually lost on the way. So host B may end up receiving a few duplicate segments, but it just discards them if they are duplicates. However, any missing parts is avoided during the transmission. And eventually, the ACK must reach host A for each individual segment that is being sent over. No matter how many times the ACK gets lost, it will keep on retransmitting the same segment over and over again.
So another thing that we have mentioned in terms of TCP is that it is connection oriented, which means that the source and destination needs to preset the conditions using which the overall transmission will be performed. So both the sender and the receiver must be ready before the communication starts transferring the data, and there are multiple parameters which needs to be negotiated and established. Most importantly, the sequence numbers and the space that we have in each direction, the starting sequence number, all of these should be negotiated with each other so that the destination knows how to count the sec and the ACK numbers. And a lot of other parameters such as the maximum segment size, if there are any other flags, any priority of the packets, all of these needs to be negotiated between the source and the destination. And this is what we call as the handshake protocol, which means that it sets up the state and the conditions under which this connection will be transferring the data. We didn't need really this kind of conditions before because in the link layer we had only 2 points, point A to point B. In the network layer we had 2 IP addresses, but now we have different applications, and different applications require different things at different times. So we need to deal with a lot of delayed and reordering of packets based on the requirement of the applications. So let's say, for example, if you are playing a YouTube video and one of the packets arrive late, your YouTube player knows that it can actually discard that packet because you have probably moved on watching that video, that particular part of the video. You don't really need to play that packet again going back. On the other hand, if you are transferring a file over the internet, it is absolutely required that the file needs to be transferred in order, and you know how to reconstruct the file at the destination. So these kind of things are required based on the application requirements, and that is why TCP is useful. Finally, when the transmission has completed, there is the final phase, what we call the connection teardown, and it allows the sender, the receiver, to basically perform a hang up which is in sync. It needs to make sure that there are no remaining packets at the sender's end which it needs to send, and also the receiver needs to confirm that it has received all the packets which were intended to be sent by the sender. So it allows what we call a symmetric termination of the connection. And although both sides shut down independently, they're not asking the other one to shut down. So it's an independent shutdown, but before that, the tear down session makes sure that the whole transmission has been completed successfully. The next concept that we talked about, one of the other very important features of TCP is flow control, which we said that it allows the sender and the receiver to be coordinated so that the sender is not really transmitting data which is faster than it could be received by the receiver. So the receiver could be a slow machine. For example, it could be a cell phone. While on the other hand, the sender is a very powerful server quality machine. So the rate of sending from the server is definitely going to be much higher than the speed at which the receiver can receive the data. So for that, TCP allows the concept of the sliding window, and that is a part also of the TCP datagram, where it specifies the number of segments which the sender is going to send out in parallel. The receiver end will then need to confirm that I can receive and I also have enough space in my buffer to receive all of these segments at the same time. If the sender says that I do not have that much space, then the sender would need to make the window smaller. If the receiver says that I have much more space available, so you can send a lot more segments at the same time, so the sender will then increase the window size, and that is how the flow control occurs with the help of TCP and is a part of the core property of the protocol. So in terms of the applications for which TCP is more suitable, we consider TCP where the guarantee of delivery is of a primary concern. And that comes with the fact that we are okay, even if it is a little slow, because we are more interested in the complete and guaranteed delivery of the data and information. The applications, for example, would be when you're browsing the internet over the HTTP protocol or the file transfer protocol, that is FTP, which allows you to transfer files. Protocols for emails, for example, SMTP, POP, or IMAP. So all of these applications are suitable for TCP applications. And to sum it up, we say that applications which require a strict order of the packets to be transmitted and also a strict ordering of the packets at the destination end, so that the receiver can effectively reconstruct the exact data that was originally at the sender's end, and then we are guaranteeing the complete delivery of the packet to the destination, and even if the latency is needed to be compromised. So we said that TCP is reliable, however, it is slow.